Let's do just a quick review. Let's get started. Something we learned in Calc 1. The fundamental theorem of calculus, parts 1 and 2, and we'll talk about a little bit of simple integration. All right, let's jump to it. So here's a bunch of hieroglyphs, right? We got the fundamental theorem of calculus, part 1. Where, wow, that seems like a lot. Look at all these words. It's a ton. But what we basically want to get from this, I'm just skipping past a lot of this. I'm just going to jump down here. So you got an integral. That's an integral. And then if you take a derivative on an integral, you end up back where you started. And I'm simplifying this way too much. Way too much. But we don't really use Ftc Part 1 all that often going into, say, a Calculus 2 class. But what we use constantly, the fundamental theorem of calculus, part 2. And I think that's where we're going to start. Because this is the integral class. How we integrate. And this is saying if you have bounds to numbers of a function, you find its antiderivative and you plug them in. So let's start with that. I could go on and on. You get that in class when we talk more about the technical side. Let's start saying how to do stuff. So I want to start with Ftc Part 2. Not Part 1, but Part 2. We use it more, so let's see it. And since we're going to use this constantly, let's make this the first thing we do. So we now have some integral with respect to x. You can tell it says dx on the outside there. And we have our integrand. Don't worry, we won't use too many fancy words, but the stuff inside of an integral is called the integrand, just like the stuff underneath a radical or a root is called the radicand. It's the stuff that's inside. But we have what's called bounds, so we're going to be finding the area under the curve. So we have some parabola here. Looks like this, huh? I don't know, maybe it's probably not perfect, not to scale. You'll be able to tell that my graphs are not the best. But we want to find the area under the curve from 0 to 3. So, right, we got some negative area right here. And then we got some nice little positive area over here. And we're going to get that area under the curve. That is what an integral with bounds is going to tell you. So let's just go to it. And I'm going to assume that nobody would be in a Calculus 2 class without knowing how to find antiderivatives, right? That's all you did in the last class was find derivatives. So let's go. The antiderivative of 3x squared. So that is going to become x cubed. And the reason is, we're going to take it, that 3 goes. The game, you add 1 to the exponent, and then you divide by the number. Next, we have 1, or x to the 0 with power. So let's add 1 to that exponent, and let's divide by that number. And then once we're done, that was the antiderivative. Hopefully the antiderivative isn't so bad for you. Once we're done, instead of writing with the integral symbol like this, we just put a straight line on the other side saying, we're done with the antiderivative. We're ready to plug in. This is Ftc Part 2. So let's clean this thing up just a tad and go, well, this is x cubed minus x. Well, I don't need those parentheses, but there you go. From 0 to 3. And this is how we're going to plug in. Now, this is my preference. You don't have to do it the way that your teacher does it. But I like to something cubed minus something cubed minus something. So on the first one right here, we're just putting in our 3's. So it's 3 cubed minus 3. Now we're going to put in our 0, our lower bound. So the upper bound goes first, the lower bound goes second, and then we get 0 cubed minus 0. So we end up with, what's that? 27 minus 3 minus nothing plus nothing. Notice how I distributed the negative because it's not always 0. And then we end up with 24, saying that the area underneath that curve was 24 units squared. But we're not going to use the unit squared. I'll let you deal with that in physics. There it is. There's our beginning. This is how we're going to integrate. You're going to do this over and over and over and over and over. Now let's just see one more. A real simple one, right? Nothing too big. We got our integrand, the stuff inside the integral. That is negative 3 divided by sine squared. And then we have some bounds going from pi over 4 to pi over 3. But this is simple stuff. This is just trigonometry. You already got that down. And it's okay if you've forgotten some stuff. I know on breaks we tend to forget quite a bit. But if you never knew this, you might have some problems. So 1 over sine squared, this is actually the same thing as negative 3 times cosecant squared of x. Now this is typically the opposite of what we like doing with trig. Usually we like sines and cosines, but we know the antiderivative of negative cosecant squared. We do. It's cotangent of x. So let's just do a little bit of work, just a little bit, and I want to use the idea that we can remove any coefficients and just drop them to the outside. I call it removing noise, but I actually just want to take the 3. And the reason why I want to just take the 3 is I know the antiderivative of negative cosecant squared. That's cotangent of x. Remember that when you had to know the derivatives of stuff? Derivative of cotangents, negative cosecant squared. So this becomes 3 cotangents of x, evaluated from pi over 4 to pi over 3. So now we have 3 times, and I like to leave the constant on the outside. Okay, so it depends on how you want to do this, but I'd rather go cotangent of minus cotangent of, and now we look, we're like, okay, put in your upper bound, pi over 3, and then put in your lower bound, pi over 4, and then it's no big deal. We just run through and we solve it, because we took a trig class, right, or pre-calculus or something like that. You got to know this stuff. So this is 1 over root 3, clearly. Cotangent pi over 4 is clearly 1. We distribute it in. It doesn't really make any difference. And that becomes root 3 minus 3. Sorry, I'm going to let you figure out why 3 over root 3 is just equal to root 3. Yeah, there we go. It's just simple stuff to start off. I'm kind of being facetious because I know we forget a lot of things. But we have to know our antiderivatives of trig functions. We got to recognize them. Got to see them. All right. Now that we've dealt with Ftc Part 2, which we're going to use over and over, let's just quickly go through Ftc Part 1. This is not used as much. Let's just run it. Now, the way I have this set up is not... This is not set up for Ftc Part 1. The idea of Ftc Part 1 is if you take a derivative of an antiderivative, you go back to where you started. So I'm going to give you an example. We don't solve it this way, but this is not yet set up as Ftc Part 1. Notice there are t's. We have to use 2 different variables, and then we have an x up top. Well, what we're going to do is, since we're saying we're going to take a derivative with respect to x on the integral. So we should just go back to where we started. The answer is going to be cosine of x. But I want to show why. So I'm just going to leave this and say, all right, we're going to take a derivative on some stuff. Okay? Now, does anybody know the antiderivative of cosine? Yeah, it's sine. It's sine. And this is, again, this is not how we do Ftc Part 1, but I want to show why it works. And now we can integrate from pi over 6 up to x. Okay, cool. So we're going to use Ftc Part 2. Wow. So let's check it out. So we say this is equal to the derivative of, and then we're going to say it's sine of something minus sine of something. Well, we just pop in our x for the first one, our upper bound, and then we put in our pi over 6 for our lower bound. Now what happens? Sorry, I'm not color coding anymore. So we have sine of x minus 1/2. Now let's take a derivative on that. The derivative of sine is cosine, and the derivative of a number is absolutely freaking nothing. Oh. So what Ftc Part 1 was telling us is if you have an x as your upper bound, and everything's a little dummy variable of t, and you're going to take a derivative on it, you could just state that it's cosine of x, not t. Now let's try another one, and then let's be done with this. But let's not do that whole long-winded thing. Yes, we can find an antiderivative on e to the t. Yes, we can find an antiderivative on negative t. But I don't want to. I want to use what the rule is saying. Saying if you take a derivative on an integral, it just works. All we're going to do, e to the minus the, and then we're going to multiply it by something. What's it going to be? just the ln of x, as long as that's up top. So this is ln of x, ln of x. But here's the trick. We got to multiply by the derivative because we're actually going to do a chain on this. We're skipping past all that work we did. You know, all this work, we're skipping past it because we can just get to the end by knowing this rule. Does anybody know the derivative of ln of x? I sure as hell hope so. So that's 1 over x. Now you leave it like this, big problems. That's bad. We mallow. Don't do that. We can clean this up. E to the ln of x. That's just x. And if you clean this up by bringing it in, we get 1 minus ln of x over x. And there's Ftc Part 1. And I know I've gone kind of quickly through this, didn't explain a lot, but you learned this in Calc 1, in Math 30. So that's how we do a real fast refresher on this, and then move right past, and we're going to get into 5.4, where we're going to learn a couple tricks about symmetry, and maybe just some fast ways to get through problems. It's called working with integrals. So, all right, I will see you in the next.